In the last lectures, we were talking about optimal binary search trees, and that was the last algorithm for dynamic programming. And let me do a quick review before I wrap that up. So this was the case where you're trying to figure out what is the optimal BST, okay, the optimal binary search tree, assuming that the frequency of search is not uniform for the different keys. Okay, so we had said that let K be the set of keys, K1 through Kn. These are distinct, and P sub I is the probability of search for a particular key. And we said that T could be any particular binary tree, and you could have a really large number of exponentially large number of binary trees corresponding to n keys, as you saw in the last lecture. And well, we said you have the cost of a tree, and that can be given by the following equation, which is basically summing up the possible different ways in which you could have the keys, the probability of that search multiplied by the depth of that key added +1. And we looked at different examples, and we saw that the complexity of this was exponential. So clearly you need to have perhaps a dynamic programming solution. And for that, the first thing that we needed to do was to make sure that it has optimal substructure, right? And we saw that it does, in fact, have optimal substructure. And we said that, well, if we define Cij to be the cost of searching for a given tree, perhaps I didn't mention this, but this is for a given tree. And we took a couple of examples and we said, well, let's take a tree with 3 keys. So you have K1, K2, and K3. And we try to see whether there is optimal substructure and to see if we can have a recursive equation for the cost of this entire tree. And we said, well, let's set K1 to be chosen as the root, and K2 initially to be chosen as the root of the substructure. Okay, so here K2 is chosen to be the root, as opposed to the second case where we said K1 is still the root of the overall tree, but K3 is now chosen as the root of the substructure. Okay, so we took 2 examples. First, this was the first one and the second one. And we said, well, if we can rewrite the cost for the entire tree, then it can be rewritten as a recursive equation. And it so happens that the recursive equation for both of these cases happens to be the same. Okay, so the cost for searching for keys 1 to 3 is turns out to be the probability of P1 of the first key plus the cost of this searching through this substructure, okay, 2 and 3. And then weighted and then added to that is the weight, the probability of either key 2 or key 3 taking place. Okay, and so we saw that this is a generic equation that you can write, and so this sort of confirmed our conjecture whether the optimal substructure exists or not. Okay, and the reason why we were able to confirm that is because the weight, regardless of whether you take T1 or T1 prime, you rearrange the substructure, the weight 2, 3 remains the same. It's basically saying the weight of 2 and 3. Yes, question? Okay, so the weight was basically, I did have an equation for that. Yeah, so here the weight is, when you say weight 2, 3, that's basically the sum of the probability of 2 and 3. Okay, so if I said weight 1, 5, then it's simply sum of the probabilities P1, P2, P3, P4, P5, which is the probability of any one of those keys being searched for. Okay. So, so basically we said that this particular, the cost from 1 to 3 can be written generically as the cost of searching for P1, K1, plus the cost of searching for the substructure 2, 3, plus the weight of 2, 3. Now, notice that the cost of 2, 3 will change depending on whether you're looking at this particular substructure or you're looking at substructure. Okay, that is the cost of that substructure. Searching through that will change. The reason is that obviously we have different probabilities for J and Z, and if their order is changed and the depth is changed, and so the cost structure will change as well. Okay, but assuming that this will be a recursive call, then you can write this generically as a recursive equation. And so if the cost of 2,3 of T1 prime is less than that of T1, then the overall cost will also be less. And so that was our contention that that would be a proof by contradiction. Okay, so we went over this in the previous lecture, and I'm not going to completely repeat that, but that's just a quick overview. Now, let's move forward from there and try to sort of generalize this to see whether we can get an equation which is sort of a more general equation. So the first thing that I'm going to represent this earlier equation, which basically said that the cost of 1 to 3 is the cost of P1. Okay, P1 is the probability that you search for key K plus 2, 3, which is the cost of the substructure plus the weight 2, 3. Now notice that weight 2, 3 and P1 can be combined and can be simply written as weight of 1, 3. That's simply of any one of the keys 1, 2, or 3 being searched for. I've written this in a slightly more concise form, which is basically saying the overall cost of this entire tree is the cost of the substructure plus the weight of all 3 of those keys. Okay, weight from 1 to 3. Okay, that's simply because I'm taking and combining these two, as you can see over here. Okay. So now, if you've understood that, now let's try to sort of generalize this and say, well, in this case, I had taken K1 to be the root, and I had a substructure which was only the right keys. Okay. Now let's try to generalize that and say, well, let's assume that you have 2 substructures, T1 and T2. T1 is the left substructure and T2 is the right substructure. And I'm making K3, which is some key in the middle, and I'm making that the root. Okay. So can somebody tell me what, based on this, what would be the equation for the total cost of searching for keys 1 through 5 based on this BST, which now has a root K3 and then substructure T1 and a substructure T2, and we're going to use a recursive solution for this. So can somebody tell me what would be the recursive solution for a more general case? So hopefully you can sort of see that we've taken the cost of, in the earlier case, we've taken the cost of the right substructure plus the weight of the entire tree. Can you sort of generalize that? Not too difficult, actually. So what now, earlier we just had one substructure, which was T1, which is a cost 2, 3, going from searching for keys K2 and K3. Now we still have that. So hopefully that's going to continue on. All right, so I could still write this component over here, which is the cost of 1 through 5 is now the cost of 4, 5. All right, so that should be a big hint. Plus something else. Oh, sorry, I didn't see your hand. Yeah. Okay, so the cost is basically, it's a recursive cost, okay? And it's basically saying that if let's say if we had to determine the cost of this, so let's go back a little bit. Okay. Let's see where are we. Okay, let's take a look at this. So the cost over here for this particular substructure, for this particular structure, is we're going to say, well, what is the cost of doing a search? Okay, and we're going to say, well, it's the cost of searching for Z. Okay, which we're going to weight that by its probability. So it's 0.1 is the probability of searching for Z. Okay, and that comes in from here, multiplied by its depth plus 1. Okay, so if you didn't have any of this and you just had Z, then the cost of that would simply be 1 times the probability of doing that search. Okay, so that comes out to be 0.1. Now the cost of searching for J in this case is the probability of J happening, which is 0.3, multiplied by how many nodes did you have to examine to get to J? Okay, so you had to examine Z, and you said, well, J is smaller than Z, so now I'm going to search to the left BST. Okay, so you had to do one search, examine one node, then you had to examine a second node, and so the total number of nodes that you had to examine were 2. Okay, and the probability of this was 0.3. So we're going to take 1 plus 1, which is essentially the number of nodes that we had to examine. So 2 times 0.3 is 0.6. Now, similarly, the cost of searching for key C is the probability of C, which is 0.6, multiplied by the number of nodes you had to examine. And so you had to examine Z, and then you had to examine J, and then eventually you had to examine C, and so you had to examine 3 nodes. Okay, so you're going to take the depth plus 1, 3 times 0.6, which is 1.8. Okay, and then you're going to sum it up because you're going to take the average cost. Okay, so that comes out to be 2.5. Okay, so this was sort of a reminder for all of us. So now essentially, so the cost is the weighted sum of searching for a particular key, weighted over all possible keys. Okay, and that's what C2, 3 means, or C1, 5 means that what is the average cost of searching for all the nodes? That's going to be weighted by the probability of searching for any particular key. All right. Versus the weight, of course, is simply the sum of the individual probabilities. It doesn't have the depth involved. Okay. So now, if you've sort of have refreshed yourselves in terms of what this cost actually means, so can now somebody still tell me what the equation is for this recursive equation where you have a left subtree and a right subtree? So C45 is basically saying, well, it should be based on this. It should still have the cost of the right subtree involved, okay, which is now going to be for keys 4 to 5. So that's the cost of searching for keys 4 and 5. Plus what else? Yes. Yes, so that should be the cost of searching for these 2 keys. Okay, so whatever the cost is, so it's going to be recursively done. Okay, anything else? Yes. Weight of 1 through 5. Yeah. So now, earlier we just had the weight of 1 to 3. Now we're going to look at the weights from 1 to 5. Okay. So I hope everybody was able to follow that. But if you followed up till here, that this extension from going to 2 subtrees hopefully should not be that difficult. All right. So if we agreed with this general equation, okay, which is the case where you're basically searching for you're given a particular tree. So C is where you're given a particular tree. So this is what I said earlier for a given tree. Okay, so the Cij's are if you're given a particular tree. and you're selecting a particular key to be the root. Okay, so in this case, I've said, well, K3, I'm selecting K3 to be the root. I'm going to make K1, K2 to be the substructure on the left side, K4, 5 to be the substructure on the right side. And so what is the estimate, the average cost of searching through this particular tree? Okay, and that's simply going to be the cost of searching through the left substructure, plus the cost of searching through the right substructure, plus the sum of the entire probabilities of this entire substructure, okay? Which doesn't necessarily have to be one, because it could be part of a much bigger structure as well, okay? So if you've understood this, now we're going to write the more general equation, which is almost the equation which is given in the book. And hopefully you should be able to see where this is coming from now. So now we're going to write, instead of C's, I'm going to write E's. Okay, so the only difference between the C cost and the E cost is that in the C case, that is the cost for a particular tree. Okay, and here now I'm going to say, well, what is the cost over all possible subtrees? Okay, and this is going to be the minimum cost. Okay, so the expected cost of searching an optimal BST over all the possible trees that you can form. So it's going to be fairly similar to C, but now we're going to have a min equation in there. Okay, so our eventual goal is to be able to find the optimal solution. Okay, so our goal is to find E1 comma N, where you have N of these. And what essentially we're going to do is we're going to say, well, let's select each one of these keys to be the root. Now, earlier what I had done in this case is I had fixed the root to be K3, okay? And we determined the cost when K3 was the root. So that's one possible BST, right? Now, what you could do is select all of these, each one of these, to be the root in turn, okay? So you could make K1 the root and determine what the cost would be for that entire subtree. Then make K2 the root and look at that cost and compare that with what happens when K1 was the root. And similarly, we select each one of these as the roots one by one. So we're going to select KR is recursively chosen as the root of the optimal subtree, okay, for this particular portion from Ki through Kj. And we're going to make R the root to vary between I through J. Okay, in other words, for example, if we made K1 the root, you would have something like this, and you would have all the possible trees with K2 to K5 being a subtree. Okay, but K1 would be the root. And since K1 is the smallest element, it will only have one substructure on the right. Okay, so you can generalize that. So now, basically what we're doing is we're making KR recursively the root. And so if KR is the root, then if you look at this equation, hopefully you can see where this equation is coming from. Okay, so this W1, 5 is now sort of being converted into the weights of all the keys from I through J. Okay, because we're looking at I through J. So in other words, if you're looking from 1 through 5, this would be converted into W1, 5. Okay. And then we're going to select each one of these to be the root. So this corresponds to K3 being the root. And we selected the left subtree, which was going from 1 to 2. Okay. So in other words, if R is the root, then the left subtree is going to go from I to R minus 1. Okay. And the right subtree is going to go from R plus 1 to J. Okay. Just like over here where R was 3, the right subtree went from R plus 1 to J, and the left subtree went from I through R minus 1. Okay. So without actually going through a formal derivation of this equation, which is done in CLRS. I think it was a little bit more intuitive to actually show you an example which was derived based on the costs, okay, of individual trees. So any confusion about this? And the weights Wi, comma j are simply the sum of all the probabilities of P going from Pi all the way to Pj. Okay. So any issues so far? Yes. The W's, yeah. So that's a good question. It's not completely intuitively obvious, right? And the way I derive this is by showing you simple examples. So let's go back to that example. Okay. So where did we start off with? Well, here is where I started off, and I said, well, let's try to do it again. Okay. So I said, well, the cost of 2, 3. Let's make sure that we understand this. So this is going to be probability of 2. Okay. Plus 2 times the probability of K3, right? Because this is one depth below. So we've got the cost of 2, 3. Now let's take a look at the cost of 1, 3. Okay. And we said, well, 1, 3 is the probability of P1, this happening. Okay. Plus 2 times P2. Okay. Why? Because P2 is now at a depth of 1. And we're adding 1 because you need to do 2 comparisons to get to 2. And then the cost of K3, of searching for K3, is now the depth plus 1, which is 3 times the probability of P3. Okay. And so this is where I said, well, can we now rewrite this as a recursive equation? You remember this from the last lecture. Okay. And so I said, well, this is the blue portion. Okay. And I'm now separating this into 2 parts, and I'm writing it as P1, which is the same over here. And I'm breaking this up into 2 parts. And one part is essentially the cost 2, 3. And the second part happens to be the weight of P2, 3. Okay. So by looking at the way we're doing the derivation of this, I'm trying to convince you that this can in general be written in the following form. Okay, so hopefully that is a refresher, right? Yeah. So it just happens to have a nice form, and you have to go back to the basics to be able to figure out why you're doing this addition of the weights. But that's, that's how the equation comes out to be. Okay. So this is the recursive solution. And now the question is, we've got a recursive solution, and that's based on the optimal substructure. And since we now know how to convert this into DP, you guys should be able to help me convert this into a dynamic programming solution. And so now, how do you go from a recursive solution to a DP solution? Sorry? Memoization, right? Somebody said that. And so in memoization, you need to figure out how do we convert this into a table, into a tabular format, and keep track of the probabilities so that we can sort of build up the solution. Okay. So now I'm just going to show you the solution, because I think you've seen quite a few of these. You've even seen some structures which are like this just in the last example. Okay. So this has a very similar structure. Okay. And let's take a look at if we can try to solve this. So this is a simple example. You've got the usual E matrix. You've got a weight matrix, and you've got another matrix which will keep track of which route was selected, which was the best solution. Okay, so that we can actually figure out what the optimal solution was. So based on this, can somebody tell me what the solution is? So let's start with 1, 1. Okay, so can somebody tell me what 1, 1 would be? And this is essentially saying that you simply have one key. Okay, That's it. The whole tree structure is just one key. So it's kind of obvious, but what should be the cost of searching for K1? Given these probabilities. The probability of searching for K1 is 0.6, and 2 is 0.3, and 3 is 0.1. So what should be this? Well, you can get the solution from here, or just intuitively you can say, well, this is what the cost should be. Okay, what should be the optimal cost of searching for K1? Yes. Yeah, so it's simply going to be 0.6 because we're simply saying that, well, how many nodes do you have to examine? That's just one node. And what's the probability of that happening? Is 0.6. So it's a weighted sum of the probabilities. So that's 0.6. Similarly, E22 would again be 0.3, because that's simply saying what's the probability of searching for K2 if that was the only node in the entire tree. Okay, so the probability of that key being searched, which is 0.3, times the number of nodes that you'd have to examine, which is simply 1, because it's right at the root. Okay, so this is going to be 0.3, and so this is also going to be 0.1. Okay, so the bottom layer was kind of easy to figure out. The weights are also kind of obvious, because weight is simply the weights of all the probabilities. So this is going to be the weight of P1. This is going to be the weight of P2, and so on. So the bottom layer happens to be identical. Okay, and there is no decision to be made, so we don't really have this portion over here for the R table. So now let's go upwards. So as you know that hopefully in dynamic programming, as you go upwards, you look at previous memoized solutions, and that should be able to help you in finding the better solutions for layers above. So let's figure out what would be 1, 2. Okay, so 1, 2 is basically saying that what would be the optimal solution if you had two keys, K1 and K2. Okay, so now what are the possible ways in which you could arrange K1 and K2? You could either have K1, K2 going this way, or you could have K2 going and K1 this way, because remember, K1 is a smaller key than K2. Okay, so K1 will have to be on the left if K2 is the root. You can't have K2 comma and K1 this way, because K1 is smaller than K2. So these are two possible tree structures. And can we figure out what would be well, how would we determine which one is better, which one has a lower cost? We would need to evaluate both of these, okay, which is essentially what we're doing. And if you figure this out, each one of these, then essentially from the graph, it turns out that you're basically looking at this versus this. Okay, so which one is smaller? Well, 0.3 is clearly smaller, but if I were to write it down, let me just write it out. So E1, 2 is the minimum of E1, and now R, we select R is equal to 1. Okay, and we'll select R is equal to 2 later on. So if we select R is equal to 1, which basically means we're making K1 the root, okay? So it's going to be the cost of E1 and R minus 1 is 0, plus ER plus 1, which is the right subtree, which is going to be R is equal to 1. So it's going to be 2, J, which is 2. Okay, I'm going to leave out the weight over here because that's common to both of these parts, versus E1, 1 plus E, now R plus 1 is 3, 2. The minimum of those two plus the weight 1, 2. Okay, so 1, 0 is 0 because j is less than I. That's 0. E2 comma 2 is this particular value, 0.3. And E1 comma 1 in this case is 0.6. E3 comma 2 is this value over here, which is 0. Okay, so basically taking the minimum of 0.3 versus 0.6. Okay, taking the minimum of these two, 0.3 is clearly the smaller one. And so the value of this particular element here is going to be 0.3 plus weight of 1 comma 2. Okay, now what's the weight of 1 comma 2? That can be derived from the W table. Okay, so weight 1 comma 2 is essentially saying that what is the sum of the weights 1 and 2. Okay, so you can simply take these two weights and sum them up. So 1 comma 2 is 0.9. Okay, what's the weight of P of W 2 comma 3? Can somebody tell me that? And can somebody tell me what are these weight tables corresponding to? 1 comma 3. So what would be the weight of W2 comma 3? Yeah. 0.4 did you say? Yeah, so that's 0.4 because that's simply adding up 0.3 and 0.1. Okay, what would be the weight 1 comma 3? Sorry, 1.3. Can somebody tell me if that's correct? So now notice that the weights are, this is here the equation for Wi comma j. So it's not exactly the sum of the lower two elements, okay? If somebody re-guess what W1 comma 3 will be. Sorry? Yeah. 3.3, so we're getting some good, nice options. 3.3, 1.3. Yes? Yeah, so it's going to be 1, right? Why is that? Because you're simply summing up these values. Okay, so simply saying, what's this probability that 1 or 2 or 3, any one of those keys is selected, and that's clearly all the possible keys, which has to be 1. Yeah. Okay. So so it's not going to be 3.3. It's not going to be 1.3. This is going to be 1. This is going to be the sum of these two. This is going to be sum of these two, and so on. Okay, so that's the weight table, weight matrix. And once you have the weight matrix, then you can calculate the E matrix. And that is now calculated by using 0.3, which was the lower of these two, plus the corresponding weight. Okay, so what does that come out to be? 1.2. Yeah. So let's work through this one. Just by looking at the weight table and the probabilities, can somebody tell me what would be the value for E 2 comma 3? So remember, we have to do a minimum of these two, and then we have to add the corresponding weight. Yes. Sorry, 0.5. Okay, so you have calculated that by looking at 0.1 plus the probability of being 2 comma 3, which is 0.4, which is exactly right. And what about for the final value over here? So this value over here. Yeah. So 1.5, and how did you get that? So say that again, you took the minimum of what? Okay, 2, 3 and 1, 2, exactly right. That was either minimum of 0.5 versus 1.2, that's 0.5. And then you added the corresponding probability, which is W1, 3, and that comes out to be 1.5. Okay. So that in fact those are the right solutions. And you might recollect that 1.5, this is the same example. We had 1.5 as the optimal solution much earlier on. I think we've got that over here. Yeah, so we had 1.5 as the optimal solution, which is matching with our analysis. Okay. So, and what about the R matrix? We need to keep track of which was the optimal solution, right? So which solution did we pick over here for 1, 1 case? So 1, 1 case. Sorry, I think I've made a mistake over here. So that should be 2 and 3. Yeah. So in the case 1, 2, which is this particular solution, we looked at both the possible R values. Okay, we looked at R is equal to 1, and then we looked at R is equal to 2, and which value was coming out to be giving us a lower cost. Was it this value or was it this? It was with R is equal to 1. Yeah. So we're going to say that R is equal to 1 was chosen at this particular juncture. Okay, and so on. So you can fill up this table. That's a little tricky to be able to figure this out, but basically is the R value which is selected. Okay, but if I just show you the solution, this is what we have. This comes out to be the final solution, and if you try to sort of figure this out, why are these values 1.2 and 0.5? You should be able to rationalize that as well. Okay, and so I've explained that over here. Well, where did 1.2 come out from? So 1.2 is basically the scenario where you had first 2 keys being selected, and there were 2 possible ways. Okay, and so we looked at the first case where R is equal to 1, and then we looked at the second case where R is equal to 2, and we looked at the minimum of 1.2 and 1.5. Okay, and so 1.2 was coming out to be smaller. All right, and the same thing in this particular scenario, you can rationalize this and double check that 0.5 is in fact the correct answer. We already did this, okay, much earlier on, so I'm not repeating that. But for these 2 cases, it's useful to be able to just double check and make sure you know what's going on. Okay, and this sort of gives you an idea as to why did we get 1.2 and 0.5. Okay, so this was I think the last example for dynamic programming that we're going to look at, and this was the more general case, which I'm not going to spend too much time on. I just mentioned this to you. This is how it's actually done in the book. But this just complicates things because they're looking at unsuccessful searches as well. Okay, and they're saying, well, you could have probabilities associated with K1 with all of these Ks, but you also have probabilities associated with unsuccessful searches. Okay, and they define this as Q sub i's. So the only difference that eventually it comes out with is that EI, J is slightly differently calculated. Okay, but I don't want to bother with that. I just want to show this to you because in case you look at the book and you say, well, the book's equations are very different from my equations. Well, the reason is because I've made it simplified and I've assumed that all of these Qs are basically equal to 0. Okay, so I'm assuming that none of these unsuccessful searches actually are valid searches, and they all have 0 probability. Sorry. Okay. So that finishes our long list of lectures on dynamic programming. And so unless there are any questions on dynamic programming in general, I'm going to start, and in the next perhaps 1.5 lectures, take a look at some different topics. Okay, so this topic simply happens to have the second term to be programming as well. But let's take a look at this. And it's quite an interesting set of problems that are really relevant if, for example, you're going to become a manager on these days. Okay, if you go on and, God forbid, go for an MBA degree, okay, and waste your computer science degree. Well, that's not necessarily true always, but sometimes, yeah, managers do use some technical background. And so if you're becoming an MBA and you have people who are doing operations research for you, this is the kind of problems that you'll ask them to solve, okay? So linear programming problem basically is a method to get the best outcome, okay? Such as, for example, maximizing your profit or lowering the cost in a model whose requirements or constraints are represented by linear relationships, okay? And that's why it's called linear programming, okay? And it's best to understand this if you look at a particular example. So let's take a look at this example. And generally, these are word problems. So you're given with a whole bunch of descriptions, and then you have to convert this into a linear programming problem, okay? And so let's take a look at this. So it says here that a company makes two types of products, okay? P1 and P2. These could be toys, it could be cars, it could be what have you, planes or what have you, okay? And given that the cost is $3, it's probably toys. So P1 sells for $3 and P2 sells for lower amount, $2, okay? Now, in addition, you'll have a bunch of constraints, okay? So let's say the following are the constraints. So P1 requires 2 hours of labor of type L1, okay? For example, L1 could be workmanship. So if you're creating a toy, let's say you have 2 types of resources, you need to get that thing actually made. And then maybe L2 is painting it, painting the toy. So, so let's say that P1 requires 2 hours of L1 type of labor, okay? And 1 hour of type 2, okay? So it takes 2 hours to make P1, takes 2 hours of L1 and 1 hour of type 2. And similarly, P2 requires 1 hour of each. Okay, so it takes 1 hour of workmanship and 1 hour of painting, for example. All right, that's the first set of constraints. Those are not constraints, but that's basically telling you how that particular product is actually manufactured. Okay, now the constraints are that you only have 100 hours of labor of type 1 available, okay, in a week. So you're trying to look for labor, and unfortunately, there's a management problem, so you only have 100 hours available. Okay, and so this is one of the constraints. Another constraint is that there's only 80 hours of labor of type 2, let's say painters available in the market, to be available per week. Okay, so those are 2 real constraints. Another constraint is that we can only sell 40 of P1 types of products. Okay. In a week, there isn't a demand for more than 40. So it's pointless making more than 40 P1 products. So the question is, how can you optimize your overall revenue? Okay, so now we need to convert this into a linear programming problem. Okay, so we can actually optimize our overall revenue. So now I need you guys to think, put on your management hats and try to figure out a solution to this problem. How could we start, how could we attack this problem? Can we convert this into a set of equations? Maybe, yeah, so one way to think about it is start from the bottom up, okay? Think about what are you trying to maximize, okay? So let's assume that we call Z as our revenue. Okay, so what is the revenue equal to? So you're making two products, P1 and P2. Yes, Jane? 3 times P1 plus 2 times P2, right? Now, P1 and P2 are actually the names of the products. So I'm going to use variables X1 and X2 to represent the actual number of P1 and P2 produced, okay? So I'm going to rewrite this as Z is equal to 3 times X1 plus 2 times X2. Okay, so X1 and X2 simply correspond to the actual number, the quantity of product P1 and P2 that you manufacturing on a weekly basis, respectively. Okay, and so you're simply multiplying it by the how much money that fetches you in the market. Okay, so now we're trying to optimize the overall revenue, and that's given by this equation. Okay, now can somebody tell me what are the constraints? Can you rewrite those constraints in terms of X1 and X2? Jack. Two X1 plus X2 is going to be less than or equal to 100. And that's based on the following equation, right? The first one, which is basically saying that 2 hours of labor of type 1. Okay, so that's 2 hours of type 1 plus 1 hour of type 2 has to be less than or equal to the total available amount of labor available for type L1. Okay, so that's clear. That's very good. And can somebody else tell me what the second equation would be? Second constraint, that's the first constraint. Second constraint. Anybody else? Not too difficult. Yeah, Thomas. Yeah, so that's the second constraint. Let's keep going. Is there a third constraint? So we've done, we've essentially done the first 4 of these. Okay, is there one more constraint? Somebody can specify that? Yeah. X1 must be less than or equal to 40, right? Because we can only sell 40 of these, okay? So that's great. You've basically rewritten this as a simple linear program, okay? So what did you do? Well, we said, well, let's define our decision variables. X1 and X2 are the quantity of P1 and P2. Yeah, yeah. Yeah, okay. So I guess that's what you were about to point out, is that they have to be positive. Is that right? Is that what you were pointing out? Yeah, okay, great. So I've rewritten this as the following constraints. So 2x1 plus x2 has to be less than 100, less than or equal to, less than or equal to 80, x1 has to be less than or equal to 40. And both of these have to be non-negative, right? You can't produce negative quantities. So you've got these resource constraints, and you're trying to maximize your profit, which is z is equal to 3 times 1 plus 2 times 2. Okay, so sorry, 2 times x2, right? Now, how should we solve this? Okay, so those are nice resource constraints and objectives. And so more generally speaking, the linear program can be written as the following set of equations. So generally, you have to maximize something or minimize something. And this, in this case, you're trying to maximize your revenue. If it was your cost, you try to minimize that, and you'd have a bunch of constraints. So you rewrite the linear program as maximize or minimize this equation subject to the following equations. Okay. So in this case, n, which is the number of decision variables, n is equal to 2. Okay, and the number of constraints that you have, which is m, is equal to 1, 2, 3, 4, 5. Okay, so you've got 5 constraints, and you've got 2 unknowns. So if you were to try to figure out what the complexity of this optimization problem is, you could venture to guess that, but I suspect you would be sort of at a loss to figure that out at this stage. Okay, and it's not completely obvious what the complexity is, but it's pretty horrendous. Okay, and that's why we need to have a good solution to this problem. So there are various solutions to this, and the most well-known solution is something called the simplex solution. Okay, simplex. And I'm not actually going to show you the simplex solution because even in CLRS, they've actually dropped that solution because it's kind of tedious. It's easy to implement it once you have a program and there are libraries available to do it. And the logic is somewhat tricky. So, and we certainly don't have time to do that. But what I will show you is a graphical solution for a simple case of two variables. So if you only have n is equal to 2, you can have a graphical solution for it. Okay, and that's something which is nice and intuitive, and it basically tells you how to solve this class of problems. It also sort of gives you a general idea of the complexity of these equations, of this optimization problem. Okay, so we're going to try to write these equations and try to draw them out as a bunch of linear of lines, right? So every linear equation can be written as a line or a shaded region. Okay, so can somebody help me show these equations on this particular graph? So the simplest would be this one over here. So let's start with that. X1 is on the horizontal axis, X2 is on the vertical axis. We're saying X1 has to be less than or equal to 40. So clearly there's a line over here, okay, and which basically saying, well, this is the region that is an acceptable solution. So anything which is X1 has less than or equal to 40, this entire region is going to be an acceptable solution. And this is generally referred to as a feasible solution, feasible region. So that is a feasible region based on simply one constraint, but now let's add on all the other constraints. Can somebody show me the other constraints? Somebody who's good at geometry, drawing two-dimensional graphs. Okay, so can somebody show me the second line? So let's do this one over here. This one is easy. What are the 2 points that I would go through? Yeah. So clearly it's going to go through these 2 points. Okay, so let's see, this is line which sort of goes like this. Okay, and the region is, it has to be less than or equal to 80, so it's going to be this particular region. Okay, so you can hopefully draw all 3 of these lines. So you'll have these 3 lines, and each one of them is basically specifying a feasible region. And so if you have to satisfy all of these constraints, then clearly it has to be the region which is satisfying all the constraints. So as hopefully you can see that this will be the region which will satisfy all 3 of these constraints. Okay. So this will eventually be called the feasible region. Remember, there are lines over here as well, which are the last 2 equations, which basically say x1 is greater than or equal to 0 and x2 is greater than or equal to 0. Now the question is, which one of these is the optimal solution? Okay, so I'm going to remove this. But now, if you're given this set of feasible region, where do you think the optimal solution will lie? And can we also draw the z equation? Okay, so we try to maximize this particular equation. So how could we represent the revenue equations, or maybe a set of lines, which can sort of take us to the solution? So any thoughts on that? Yes. Okay, very good, excellent. So the suggestion is that let's draw out straight lines for constant values of z. Okay, so we can use the following equation where, let's say, 3x1 plus 2x2 is equal to some constant. So let's pick some constant value. Let's draw it out for about for 60. Or you could use 30 as well. Let's start it off with 30. All right. So what would be the 2 points where this particular equation would go through? We can set either one of them to be 0 and figure out the 2 points. So if x1 is 0, then x2 is going to be 15. So it's going to go through this particular point. And when x2 is 0, x1 is going to go through 10. So it's going to be a straight line going sort of like that, right? And this is for profit of, for a revenue which is equal to 30, right? Now, clearly, you can do better than that and still remain within the feasible region. So let's double this and say, well, now we're going to have 20 and 30. Let's take a look at this particular line. It's going to through 20 and 30. So this would be another line, and this would be with revenue of z is equal to 30. So you can see that if you can create parallel profit lines or revenue lines, and you can sort of keep on pushing them further and further away, then at some point, you're going to find a particular vertex of this particular, you can call this a polyhedron. Okay, so you can see that this is a particular geometric shape. Okay, it has vertices 1, 2, 3, 4, 5. So it's a geometric shape with 5 vertices. And from the look of it, can you just look at it and tell me where would the optimal solution lie? As we're pushing this profitability curve further and further away, we instead of having revenue of 30, this is actually a revenue of 60. Sorry, right? So this was revenue of 30. This was revenue of 60. Why is that? Because for 20 times x1 being 20, you have 3 times 20, which is 60. Or if you have this particular point, that's 30 times 2, which is 60. Okay. So can somebody just looking at the solution, looking at this geometric process, can you figure out? Well, my first question is, will the solution lie in the center of this feasible region, or will it lie on one of the vertices? Yes. Yeah, so it should hopefully lie at one of the vertices. It's possible that this particular line is parallel to one of these constraints, in which case it would lie on the whole line. Okay, so if these two lines were parallel to each other, then it could actually possibly be that entire line could be the set of possible solutions. Okay, but since it doesn't seem to be parallel, okay, and so it's kind of hard to guess because these two lines are fairly close to each other. But let me just show you the actual result. This is how these lines are. The dotted lines are ones which are showing you the different values of z. Okay, so this is the line where z is maximum, and you can see that it's intersecting with that earlier geometric shape at this particular point where x1 is equal to 20, x2 is equal to 60, and in that case, what is your total revenue? Can somebody tell me what the revenue would be? So 3 times x1 would be 3 times 20 plus 2 times 60. That's 60 plus 60 plus 120. That's 180. Right? So this particular line over here corresponds to a revenue Z of 180. Okay. So geometrically speaking, this is relatively easy to figure out. Okay. But if you think about the complexity of this process, if you now think about what happens when you have n is equal to 3. What do you think the geometric shape would look like? So this was a two-dimensional shape. Okay, so this was the solution for a two-dimensional shape. Okay, so this is the feasible region, which I've shown over here in tan. Okay, this was the optimal solution. These were the different set of constraints. Okay, and if x1, x2 were not the only variables, and you had a third variable, x3, then what would this shape look like? Yeah, there would be some 3D shape, right? So it would be some kind of a complex 3D shape. Yeah. Yes, yes, certainly. Well, the fourth dimension doesn't necessarily come in, okay? And there's some really nice graphics, which I don't have right now for you, but you can go on YouTube and try to visualize, a three-dimensional problem, linear programming problem. But basically what you would have, for example, if you had a square, okay? So if I can try to show you this shape, all right? So here's a three-dimensional shape, okay? And now instead of the Z lines being a single line, what would they be? Where the profit is constant, where the revenue is constant. It would be a plane, right? So now you have a three-dimensional shape, which is being cut into two halves, okay? With a plane, okay? So these lines would be plane lines, and then you would sort of take that planar line and make it go as far as possible. Okay. Now the simplex solution, which I'll just tell you how it goes. Okay. The simplex solution basically says, well, I'm going to start off at this particular point. Okay. And part of the solution, the process by which the solution comes in is to say that the solution will always be at a vertex, which is something that was sort of guessed at earlier, okay? It's going to be at one vertex, or it's going to be at a set of vertices, okay? So it could be at this and this vertex, but in any case, the solution one of the vertices will always be the optimal solution. So one possible way of solving this problem is to search through all the possible vertices, okay? But the number of vertices, and this is a three-dimensional structure,